Я рад вас всех приветствовать здесь на нашем научном семинаре, или точнее лекции почетного доктора МЭИ. Это единственный почетный доктор, который реально защитил докторскую диссертацию в стенах МЭИ. Более 10 лет назад был его доклад научный в малом актовом зале МЭИ. И сегодня он к нам приехал и любезно согласился прочитать нам лекцию, исходя из своего очень большого опыта. Опыта у него на самом деле много. Я надеюсь, каждый из вас прочитал краткую автобиографию о нем. Кто-то знает, кто-то нет. И его основная задача, что я хотел вам сказать, его основная задача для приезда – это проверка готовности Московского медицинского института к проведению ежегодной встречи Международной ассоциации по свойствам воды и водяного пара, в работе которой эта организация, наш институт очень много, скажем так, времени уже уделяет, был одним из основателей, и очень много профессоров, студентов, аспирантов нашего института работало в этой организации. Доктор Барри Dooley, исполнительный секретарь этой организации, то есть уже в течение более 20 лет. Он, скажем так, ответственное лицо за проведение. И что еще хотел самое главное отметить, и как раз передам, скажем так, слово более знакомому человеку, который очень долго с ним работал, это президент этой ассоциации по свойствам водяного пара, это профессор нашего университета Тамара Ивановна Петрова. Пожалуйста.
Я не буду вас задерживать долго. Значит, Берри является одним из крупнейших специалистов в области водного режима и вот подготовки на тепловых станциях разных типов, на станциях с обычным оборудованием и на станциях с парогазовыми установками. Он специалист в области подготовки воды, в области водного режима и в области химконтроля. Наш институт и наша кафедра, в частности, имеет тесную с ним связь с 1992 года, то есть это в прошлом столетии. Мы работали в течение примерно 15 лет, очень тесно. Он в то время работал, есть в Америке такой ведущий институт в области энергетики, это Electrical Power Research Institute. И в рамках этого института и нашего института было 3 контракта, задача которых состояла одного контракта изучить то, что происходит в паровых турбинах, почему вылетают иногда лопатки. Вот студентам 4-го курса я показывала, что может быть в результате этого. И второй вопрос – это вопрос образования отложений и как влияет водно-химический режим на процессы образования отложений. Ну, работа эта была плодотворная, результаты вошли уже в классику, и мы продолжаем сотрудничать, и сейчас уже Берри работает совершенно другой организацией, но тем не менее сотрудничество очень такое активное и в области науки, и в области Международной ассоциации по свойствам воды и водяного пара. Есть вопросы? Берри, please.
Please. Okay. Good afternoon. Good afternoon. Hello to everybody. We're supposed to say hello. Hello.
Hello.
Hello. Thank you. So everybody can everybody understand English?
Yes.
Okay?
Yes.
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 Yes. What about this side? Okay. So the first thing we do is turn our phones off. Please turn the phone off.
Ready.
And then it won't ring or vibrate. Yes?
Yes.
So it's off. Now, I don't speak any Russian other than a few words. How to ask for a beer, I know that. I know how to say good morning and good afternoon, but nothing very much else. So I have no idea what Tamara then said or Constantine, but I assume they made an introduction. And I don't know who you are, so I assume that you're students in the chemistry department, is that correct?
Department of water treatment.
Yeah, TWT department. So you will be the future chemists in power plants in Russia and maybe in other countries, yes?
Yes.
Yes. And so this is a very good opportunity to meet you so that you can learn some very important lessons, I think. Because as Tamara indicated, I have been involved in power plants for many years and involved mainly in the research to understand the processes in the chemistry of the power plant much better than they were. And I've done that for 30 years, including some important work here at NIU. And what I want to show you today is a little bit of history, for maybe 30 years, of the history of psychochemistry in power plants. In my opinion, the psychochemistry is the most important aspect in a power plant, in a fossil plant or in a combined cycle plant. If the chemistry isn't correct, the power plant doesn't work properly. If the power plant isn't correct and optimized, the power plant will fail. And I deal with failures all over the world. In nearly all countries of the world, I get called for help with failures. So, in my opinion, the chemistry is the most important aspect. And so, research that has been done for the last 30 years has led to a much better understanding of how a power plant works and all the aspects of psychochemistry. But it does not necessarily lead to better performance of the power plant. And that's a very unusual situation in that we do research for 30 years to make an understanding much better, but it doesn't necessarily lead to an improved performance, improved availability, improved reliability in the power plant itself. And so I want you to think about that, because we believe that the solution to that disconnect is in your hands, is in the hands of the people who are in the chemists. And why is that? That is because I'm going to tell you at the beginning what the main message will be right at the end. The main message is that when you go to a power plant to work as the chemist, most often you forget about the basics of chemistry that you learn here at the university. And we find that all over the world. The main reason that power plants fail is because the basics of power plant chemistry are not applied in practice. And so I want you to think about that all the way through here. I'm going to talk for about an hour probably, but you will see that those features that are in your hands, I call them the management aspects, or the basics of power plant chemistry. There's 10 of them. There's 10 basics of power plant chemistry that you are presumably taught here in the university. But you need to remember those when you go out into the plant. And if you forget them and you don't do them, then the power plant will fail. Absolutely no doubt about it. So what I want to do is I want to, first of all, show you where the industry was about 30 years ago. And then I want to very quickly tell you about some of the research that is being done in many places in the world, including here in the ex-Soviet part of the country and in Russia, but all over the world. Okay? So if we think about the situation 30 years ago, so this is in the early 80s here, I conducted many surveys of a large number of power plants all over the world. And these were the main psychochemistry problems that existed at that time. Okay? And the first one involves the use of both copper alloys and carbon steel or iron-based materials. And it was very difficult to have those in the same power plant and get some success. So this was a major item. 30-something years ago, of how we stored the equipment, how we shut the equipment down and protected it when it was shut down. And you'll see today that that's still a very important aspect. The instrumentation that you have on the power plant to identify the conductivity, the sodium, the pH, or whatever, was also deficient. There wasn't enough training of the staff, and there was inadequate management attention. So this is when you go to the power plant, you're going to be a little chemist in the power plant, and there's going to be a big manager. And you've got to be able to convince that big manager that the chemistry is the most important thing in the plant. And I can tell you right now, it's impossible for you to do it unless you have a management process in place that involves that plant manager. The plant manager is just as important as the chemist in the plant. Okay? So these were the items that we found 30 years ago were the most important from a psychochemistry point of view. And if you look at the corrosion problems that were in those power plants, and these are the items at the same time in the early 1980s. Air in leakage into the cycle. So that means that air that comes in, not only oxygen but CO2, that comes into the condensate part of the plant, in through the condenser or the steam turbine. The plants at this time were just starting to cycle, or to be needed every day and shut down every night. So they were cycling. Condenser tube leaks and the corrosion associated with them. Instrumentation again. A steam turbine, corrosion fatigue and stress corrosion cracking. These were the biggest problems in the steam turbine at that time. And then the various boiler corrosion mechanisms. So you can see that this is where we were 30 years ago. And we had to move forward from these situations to try to do the research to understand what was needed so that we could improve, hopefully, the reliability of the plants. And at the same time, there was many sets of guidelines that were in existence. And there was no international consensus. And I just chose here four particular sets of guidelines, and I don't know whether you go into this when you in the classes that you have here, but these were the four main guidelines that existed in the world 30 years ago. This is in Germany. This is from an organization in Germany. This is in Japan, the Japanese standard in Japan. This is in the CGB in England. This was the largest utility, the largest number of power plants in the world at the time. And then this was EPRI in the United States. But I always ask the people at the back the questions. So those at the back will get the questions, okay? So in the 1980s there was four sets of guidelines, and they're these, and they were all different. There were different philosophy in each one of them. In Germany, they had already moved to adding oxygen to the plants for the chemistry, and it's this one here, combined water treatment. It means you add some oxygen to the plant, and they preferred sodium hydroxide in the drums. In Japan, they preferred phosphate in all their drum units, and they operated all their units under reducing treatments. That means they added a reducing agent such as hydrazine or oxygen scavenger. I don't know what you call it here, but one of those. And then in the CEGB in England, they operated with sodium hydroxide. And in EPRI, this was the first guideline that I developed when I was at EPRI. They had all the different units added reducing agent at this time. There was no oxygen. So you can see just across these various countries, most of the world, there was no agreement, basically no agreement on what the best chemistry was, what the optimum chemistry was for these power plants. And so we had to move away. We had to move away from this situation. And so these were the reliability issues at the time. The use of these guidelines caused problems in the plant, failures. The number one problem in almost every plant in the world were boiler tube failures, and most of them were influenced by the chemistry. I'll show you in a minute. Steam turbine blades and discs in the low pressure part of the plant. That was the major problem that occurred in the steam turbine. And every one of those was influenced by the chemistry. I emphasize, every one of them was influenced by the chemistry. Condenser tubes, feed water heaters, and then flow accelerated corrosion was not known as flow accelerated corrosion then, it was known as erosion corrosion. And at this time, in the early 80s, nobody had been killed in any of the plants because of FAC. Now, as you probably know, many people have been killed because of this mechanism, FAC, which is totally 100% controlled by the chemistry. 100% controlled by the chemistry. So these were the reliability problems that existed. These were the tube failure mechanisms that took place. This is the ranking order of boiler tube failure mechanisms. And this one, corrosion fatigue, and all of these on the number 5 here, are all influenced by the chemistry. They're all controlled by the chemistry that people like you control in the power plants. And this is in the steam turbine. So this is the in the low pressure part of the steam turbine, and these are the blade rows. The total number of outages here, and you can see that the next to last blade, the next to last stage, which we call L-1. This is the last stage. This is the next to last stage. This stage was the most important in terms of failure mechanism. And that's because the chemistry changes very drastically in that part of the cycle, but again controlled by the chemistry from the plant. And so in this time, in the middle of the 80s, I developed this little cartoon to try to illustrate that there was a problem. So this is Mr. Power Plant here, and he's cycling, you see. It's a cycling power plant, and he was eating all this terrible chemistry, because it wasn't controlled very well. So I actually had him eating here. This is hydrazine, which is a reducing agent. And he was not very happy guy. Right? The power plants were not very happy at this time. Okay? And so I tried to illustrate to people like you at the time that all of these problems, chemistry influenced problems, are in your hands. And we have to do something in terms of research. So then, in the beginning of the 1980s, we started to do some research to try to understand what was going on. But we had to recognize that there was already a very large amount of research that had already been done by some very famous people in the world. Many of them came from here in Moscow. And I put a little slide together here. I call these the mountains of the industry. That's very important people. And so I think that many of you will recognize these names, I hope, yes? Martinova, she was the head of the department here at TWT for many years. Her husband, Stirakovich, was an academician here. Mikhail Schitzman was a good friend of mine at the NIM Institute in Moscow. And Vasilenko, he was at TKTE in St. Petersburg. And these people did a lot of research to help us to try to understand what was happening in the power plant. In the United States, there was a couple also. There was this gentleman, Fred Pocock, and this guy, Grabowski, who were very famous boiler chemists. They worked for boiler manufacturers. This one for Babcock and Wilcox, and this one for combustion engineering. And then there was two people in the steam turbine area. This was very famous, Bill Lindsay and Cohen. And they were involved in the steam turbine plant. And then in the UK, where most of the boiler research was done, there was these two gentlemen, Potter and Mann, very famous. You probably learn about those in the boiler corrosion that you do here at your university. And then in Germany, there were some real excellent pioneers, Fryer and Resch, Efforts and Bonsai. And these were the people that understood magnetite that grows in the feed water part of the cycle, and how we could move from a reducing treatment to an oxidizing treatment, which is one of the real major steps that's been made. And then there was a couple of others here. Albert Persig, you probably know, and Bob Swoboda. They were involved in steam turbine plants. So there was some really excellent work that had been done, but wasn't being translated into improving the power plants. And a couple of them here. I'm sure that your teachers here, your professors, Laura Petrova here, and others have shown you these many times. But these were some of the mountains that were in the industry. And this is called we call it the ray diagram in English. I don't know whether you call it the same in Russian. We call it the ray diagram. And this was developed here, just along the corridor, I think, right? Just along the corridor here by people who worked here. And the idea was to try to help us understand if you have some impurities in the boiler, what goes into the steam. And so you can see it's against pressure, and each one of these compounds were typical compounds. And this was in existence for maybe 30 years until further research was done to improve it, which I'll show you a little later. But this really helped us in the 60s and 70s and 80s to start to understand how those impurities went into the steam. And then there was also, again, by the same people here, the various compounds that deposit onto steam turbine blades. And most of you will recognize that these are chloride here is not a very nice compound on a steam turbine. And this shows you the solubility of them, and so that we could start to understand which compounds would come out on the steam turbine and could possibly be causing a problem in the steam turbine. And this was a major piece of work that was done by Bill Lindsay and Otakar Jonas here to superimpose the chemistry on the thermodynamics. So many of you will recognize on the bottom here the Mollier diagram. So you can see here's the saturation line. And this shows the expansion through the low pressure steam turbine. So the area that I showed you before that has all the major problems occurs just about here. And so there was a thought that we could superimpose the chemistry on this thermodynamics. It turns out that it wasn't quite correct, and we know that from the work that was done later. But this was a major piece of work that was done back in the 1970s and 1980s. And this was the work that was done on copper to understand why you couldn't have any copper in supercritical units. There was quite a number of units here around at Moscow in some of the supercritical units that had copper in them, and some of that copper ended up on the steam turbine and caused many problems. But the work of Pocock here in 1963 showed that as the pressure reduces, these cupric and cuprous oxides lose their solubility. And so right down here, around 24 or 2500 psi, which is about 17 megapascals, the copper can't remain in steam. It has to deposit out. And so this is a major understanding, and this piece of work essentially removed the copper from supercritical units to say that you can't have copper in supercritical units in the feed water. And this was a very famous conference that took place. This is hydrazine, which is the main reducing agent, developed in Germany during the last war. But there was a need for this conference in the end of the 1950s here to try to tell power plants how it could be used and where it could be used. And if you get a copy of this book, I'm sure Tamara has a copy of it, but if you get a copy of this book, it basically tells you what you need to know about using reducing agents in the plant. But again, it's one of the basics that was totally forgotten. So by the time the 1980s came, all of this work was basically forgotten. And the use of this chemical, this hydrazine, chemical, was essentially used incorrectly. And that was part of why all those failures took place, because it could not control the corrosion of the iron in the feed water part of the cycle. And so that was just a little bit of the background. Now what I want to do is just do the same and just highlight a few of the items that have been dealt with from a research point of view since the 1980s. And I'll go through about 4 or 5 of these just to illustrate to you. And I don't need to go down the list, so I'll just go into here. But the point was that all of these required extensive R&D. So that means that research was done in the laboratory, and then we applied it in the field. So the first one was in the feed water part of the plant. So in that time period that I was talking about before, in the early 80s, and in the countries that I showed you, in Japan, and in the United States, and in Canada, and in South Africa, and most of the world, with the exception of Germany and a little bit of the old Soviet Union, everybody operated with the same chemistry, with the same volatile treatment, adding a reducing agent, irrespective of what the materials were. And so it became very clear that you couldn't do that. And so that we had to introduce different chemistries, and we call them very specifically a reducing chemistry and an oxidizing chemistry. So oxidizing chemistry means that you don't have a reducing agent there to make it electrochemically reducing, and you can add oxygen so that it will make it oxidizing. And then you have to know specifically which materials you can put in those different chemistries. And all that was worked out in the late 1980s and early 1990s. And it was started in Germany, here as it says, in the late 1960s by the introduction of oxygen. These two chemistries here essentially add oxygen to the cycle to make them oxidizing. And then that was applied in the early 1970s, first of all in a plant here just close to Moscow, in the old Soviet Union. This started it. But the real application in the power plants was done actually in South Africa. This here is one of the first validations of this O for oxidizing and R for reducing. I developed these names in the late 1980s and 1990s. And they're used pretty much everywhere in the world. Anywhere you go, people know that ABTO means there's no reducing agent, it's oxidizing treatment. And they know that if you have the R here, this is a reducing treatment, and you add a reducing agent or an oxygen scavenger. And there's a very big difference. And it was shown here by these two people, Vinnie Coombe and Platt, and Barry Conlon, who at least Tamara will remember, from South Africa in 1994. And this shows that this is the time here, and the green line is the amount of reducing agent in the cycle. So when we started this, there was a high amount of reducing agent, and the iron, which is the red, was very high. You can see here's the iron level, 14 or 15 ppbs. And as this reducing agent was removed from the cycle down to 0, as it goes down here like this, you can see that the iron level follows it exactly. So this was the validation for the use of this R and the O treatment. And it showed you could measure it electrochemically. You can see this yellow here is the potential. So when you have a lot of hydrazine and a small amount of oxygen, you have a reducing potential. And as that hydrazine reduces and the oxygen stays the same, you don't do anything else, this potential increases. And it changes over to oxidizing right here, and it reduces the amount of iron that's transported. And this was one of the major steps that was made in the world to control the feed water part of the plant. And by the mid-1990s, this was published by myself and a couple of other people here in 1990. We had eventually come to the understanding that there had to be, the red box here is for the reducing chemistry, and the white box is for oxidizing chemistry. And so this one means that when you have this reducing chemistry, you're adding a reducing agent, hydrazine or another chemical like that. If you measure the potential, it's reducing, not oxidizing, and this protects the copper alloys, as you'll see a little later. But it's very bad for the iron, for the iron compounds, because it increases the amount of corrosion. The complete opposite of what was thought in most of the power plants of the world. Okay? Whereas if you want to protect the carbon steel materials, the iron materials, you have to go to something in the green box here, which we call, again, this O here. So you just take out the reducing agent, the potential goes oxidizing, or then you can actually add oxygen, and we now call this oxygenated treatment. And so these two sets of reducing and oxidizing chemistry have been one of the major steps that's been made. We still see a few mistakes around the world that people don't realize, that you have to adjust the chemistry for the materials that are in the cycle. And we'll still have units that have copper in them operating under oxidizing conditions, or we'll have all ferrous systems with no copper operating with a reducing agent. And we still see that in quite a few places around the world, because the technology takes such a long time to penetrate into the power plants. So this is quite important. So the next one is about phosphate. The second area is about phosphate that's used in the boilers. And so as it says here, this is the most widely used treatment. Phosphate is the most widely used treatment in drum boilers around the world. But it's taken something like 40 years to develop a phosphate treatment that works. And this just shows you the history here. They all have very different names, and I don't know whether tomorrow these are the same in Russia or not. But so there's coordinated phosphate, which used sodium and phosphate molar ratio greater than 3. But when you use sodium phosphate ratio greater than 3, you have a high amount of free hydroxide, and that free hydroxide results in tube failures. So this one was incorrect. And so the next step was to go completely opposite, and to go to a sodium to phosphate molar ratio of less than 3, less than 2.8, and this is called congruent phosphate, and this resulted in another failure mechanism called acid phosphate corrosion. So this one was wrong as well. And so then in the 1980s, 1990s, there was a couple of treatments here, one called equilibrium phosphate and one called phosphate continuum, where the sodium phosphate molar ratio was greater than 3, but did not allow the sodium hydroxide to be too high. And actually it was kept at 1 ppm right here. And what happened then was we found out that there wasn't enough phosphate in the boiler, and so it resulted in another failure mechanism called hydrogen damage. And only just recently, within the last 5 or 6 years, have we developed this one, phosphate treatment, and this is the latest one that's in the IAPS documents. And you can see, it's probably easier just to see it here on a diagram like this. So here you're showing, this is pH here, this is a pH phosphate control box, and these lines here are the molar ratio lines. So this one here, as you can see, is sodium to phosphate 2.8. So if you operate below this, and you operate in this box, you end up with a failure mechanism like this. And this was a very common failure mechanism in the 90s, in the 1990s. And then, as I mentioned, they changed to this very low level of phosphate treatment right here in this box. And then there wasn't enough phosphate to provide protection, and it ended up with failures like this. So this was a very common failure mechanism, still is, called hydrogen damage. And so within the international community now that Tamara and Konstantin are part of, we've just developed the latest document, which we call the International Standard through IAPS. This is International Association for the Properties of Water and Steam. Russia is a member of that. And we developed this treatment here. Again, this is a pH, and this is phosphate. And you can see now that it's bounded by, it says, don't operate with too low level of phosphate here. In fact, try not to operate less than 0.3. If you operate less than 0.3, you'll end up with a failure mechanism. Don't operate below the sodium to phosphate molar ratio line of 3 here. If you operate down here, you'll end up with another failure mechanism called acid phosphate corrosion. And don't operate above this sodium, this line, which is trisodium phosphate plus 1 ppm of sodium hydroxide. If you operate above this line, then you'll end up with another failure mechanism. So operating with phosphate treatment requires very careful monitoring so that you operate within the right range, because if you don't, you'll end up with failure. And that's one of the things that's in your hands as the chemist, one of the basic things that you need to be involved in. So the next one is the steam turbine. So these are steam turbine blades in the low pressure part of the plant. And I think you recognize that there should be a blade here, right? And this blade has failed, and it's failed for a mechanism called corrosion fatigue. And here's another one here. There should be a blade here. This is also a fail. This is failed because of stress corrosion cracking. And these are the largest problems in the steam turbine. And again, totally controlled by the chemistry. And it had become clear in the 1980s here, like I showed you before, that the previous research that had been done hadn't been done properly and had not identified exactly what the environment was, and what the chemistry environment was in that particular location. And so we needed a detailed understanding of what the environment was. And so we formed an international collaboration of 23 organizations. NIU was one of them. And we did a lot of research here. But there was 23 countries in the world that were involved in it to try to work out what the environment was. And there was 3 things that we needed to do. First of all, as you cross the saturation line, you go from superheated steam to moist steam. We wanted to know how that took place. And then you have the formation of that liquid on the blade surface, that's called a liquid film, and we wanted to know what the composition of that was. And then we wanted to know what the mechanism was that actually took place. And so the work took place over a large number of years. Tomorrow, more than 10 years we worked on it, right? More than 10 years here in the steam turbine facility that you have here. And so It was conducted, some of it was conducted at the Moscow Power Institute here, and some of it was conducted in the Academy of Science in the Ukraine, plus these 23 organizations around the world. And the work that was done enabled us to identify how that moisture forms as it crosses the saturation point. It forms on ions in the flow, and it forms heterogeneously on those ions. And they have an increase in concentration. So if you have a small amount of chloride in the superheated steam, then as it crosses the saturation line, as it goes into that phase transition zone, these little droplets have quite high levels of chloride and sulfate. Okay? And they have essentially no oxygen in them. And then the liquid, so you could see these concentration factors. So whatever the level is in steam, very low levels, like 1 or 2 ppb, we want the chloride and sulfate to be in the superheated steam. The liquid that forms is highly concentrated in chloride and sulfate. And we worked out what the chemistry was as it says here. And the most important thing that we identified or confirmed, and that was confirmed here, was that in these little droplets and in the liquid that forms in the steam turbine in the low pressure part, there's no oxygen. Basically no oxygen at all. And that was really important because all the previous work that had been done, all the experimental work that had been done, did it in saturated solutions of oxygen. And so that's why the results, the previous research that was done, was not correct because it had been done in the wrong environments. So when you start to do it in the right environment that we've actually measured, then you can understand exactly what happens. And so the liquid films that form on the blade surfaces are the drivers for those failure mechanisms. And we needed to measure those. And so my good friend, Professor Povarov, who was in ran the steam turbine group here, designed some very special equipment to measure that liquid film on the blade. And we could extract the liquid films on the blade, and we could measure the composition of them. And again, we found that there was no oxygen in them, and they had a concentration factor. And so now, after 10 years of research, we knew pretty much everything that was taking place in the steam turbine, in the low pressure segment. And so then we could go on and work on the mechanisms themselves. So again, I developed a little cartoon here just to show. So here's a couple of blades in this phase transition zone. This might be the L-1 region. The superheated steam comes through and it nucleates droplets. We measure these droplets between rotating and stationary blades. We measured the composition of them, we measured the size of them, we measured the electrochemistry of them, we measured the electrostatic potential of them, pretty much everything. And they were very small, you can see right here. And then they impinged upon the blade surface. And this is the liquid film on the blade surface. And we measured that, we measured the size of it, the composition of it, pretty much everything about it. And we knew that it was about 120 microns in thickness, and we knew the composition of it. And as this flows off the blade here, it breaks up and gives rise to little droplets that are a little higher. So you have a large amount of very small droplets and a small amount of very large droplets coming off the blade here. So we basically knew everything about what was happening in this area of the turbine. And so then we could go on and work out what the mechanism was. And this is where there was an absolute major breakthrough that took place. And it was published here, originally in 1999, but it was published at the meeting in Tokyo in 2004. And the major step was this, is that the failure mechanisms that take place in the steam turbine are controlled by what happens when the unit is shut down, when no protection is provided to the steam turbine. And that's the thing that initiates the pits on the blade surfaces. If you don't provide protection during the shutdown, you end up with pits on the surface, and then those pits can grow in the liquid films that I just showed you. So then you know pretty much everything about it. But it was the turbine operates obviously, and it rotates, but it's also shut down. And so it was this part over here that was actually causing these blades to fail. The shutdown part of not providing any shutdown protection. So now we know basically what to do to provide that protection during the shutdown. And it's shown just here. This is the work that was done in the early 2000s to show this. And this here shows the probability of failure against the oxygen in the liquid film. And so during the shutdown period, and with no protection, those liquid films become saturated in oxygen. So that's about 7 or 8 ppm over here. And this is the probability of failure. But if you provide protection during the shutdown by providing dehumidified air to that part of the cycle, then the amount of oxygen in that liquid on the surface is very low. And it's down here somewhere. And so you can see that as you come down here and you reduce the amount of oxygen that's in that liquid film during the shutdown, then you reduce the probability of failure. And it's an enormous amount. It's like more than 3 orders of magnitude that you've changed the risk of having damage in the steam turbine, just by providing protection during the shutdown period. So, in every case that we look at now, wherever it is, anywhere in the world, you can always see these pits. These are pits on blade surfaces, and these pits are formed during the shutdown. And these pits, you can see if you look carefully, initiate every single failure that takes place. Right here, you can see a very good example right here, but it's these pits that essentially initiate the failures in the steam turbine. So, now the HRSGs, we're going to talk about those tomorrow with a different group, but these are from the combined cycle plants. And originally, it was thought that these were very simple plants, that we could just apply the same chemistries that we have in the conventional fossil plants. It turned out that you can't do that. That you have to look at the plant as an absolute whole. So again, I don't know whether you do anything with. Do they do anything with combined cycle plants tomorrow?
No.
Okay. So I won't spend too much time on this. Okay. But there's basically 2 types. There's what's called the horizontal gas path system. The gas turbine is here, and this is the boiler. Or there's a vertical system where there's a gas turbine here, and the exhaust from the gas turbine flows over these different surfaces. And I'll move on here. So we know now through the IOPS organization what the optimum chemistry should be for these plants. So we missed this one. And come to this one on copper. So this is the HP part of the cycle now in the turbine. And you can see these little flakes of copper. So that's the copper that's in the feed water, and that's the copper that's been mistreated by the use of that hydrazine that I talked about before. Not using the right chemistry, not using ABTR or ABTO, and controlling the chemistry properly. And so this has all been worked out as well. And that took about 15 years to work out exactly how to control this part of the cycle. And I'll just go through this quickly. This is what the deposits look like. The crystals, they grow. They actually grow on the turbine surface because of the solubility. They lose the solubility, like I showed you before. And so when you do the corrosion studies, these were done in a scanning electron microscope. If you use reducing treatment, that's with a reducing agent, you can see the surfaces here are reasonably nice and smooth. Rather low corrosion rate, but if you use an oxidizing treatment with a copper alloy, you can see what happens here. The surface becomes much rougher here, and the amount of corrosion that takes place increases drastically. And so this just validates again that if you have any copper in the cycle, you've got to operate under reducing conditions. Feed water has to be reduced. So I'll move on here. So the last part I want to look at is just to come full circle now. I showed you before the ray diagram that Martinova developed, but what we found when we actually measured the composition in steam, we found that it didn't agree exactly, and it needed another piece of research to put it all together, and we essentially developed this. This was done at Oak Ridge National Laboratory. It was done as an international collaboration again, and 10 countries supported it, and it was, so you can see now all the different compounds right here that exist in the boiler and how they partition into the steam. And we needed to know this because this is what protects the steam turbine from high levels of contaminant in the site. And again, this was a major step forward, a major iteration on the ray diagram, because it now allowed us to be able to identify what the compounds were that went into the steam. It was thought previously that if you had chloride in the boiler, that the chloride would go into the steam as sodium chloride or ammonium chloride. But in fact, it doesn't. It goes into steam, as you can see here, as HCl. So the higher up you are on this diagram, the more likely it is to go into the steam. And so you can see down here that sodium chloride is much lower. I can't see it actually. But chloride and sulfate are much lower than the HCl and the SO2 as they go into the steam. So we were able to identify how these compounds actually get into the steam and exactly what they are. So that was 5 or 6 very quick items. Now I want to come to you. See if you've been paying attention. Okay? And so many of the uncertainties identified in the 1980s have been looked at, have been consolidated, research has been done, and we now have very good understanding of nearly all of those items that I mentioned, and all of those problems that existed in the 1980s. We now have much better and closer international agreement on how power plants should operate. And this is basically because the IAPS organization has put out a set of guidelines, which is basically the international standard. And the other organizations in the world now are essentially using those same standards and changing their guidance. So we're hoping that all the plants in Russia, for instance, will use the IAPS guidelines, as they do in Germany and in the US and in Japan. And we're trying to get all the manufacturers in the world of boilers and turbines and HRSGs to use these IAPS standards based on all this research that's been done, so that we have some conformity, so that we won't have the problems in the future. That's our aim or our goal, but our aim and our goal doesn't always happen, okay, as you know. And so during the previous periods of 1990, we introduced into the world a management system to allow people like yourselves, the chemists, to have a little bit more authority in the plant and to be part of an overall team that was supported by the management, with a management directive, a management mandate, and with a corporate philosophy that says this is how we're going to do business. So then, if you as a chemist had some problem, you were part of the team. You weren't just this little minnow at the bottom. You weren't just this little fish at the bottom that had no power whatsoever. And so these programs were very, very successful in the 1990s and 2000s. But in the mid 2000s, we dropped them. We didn't keep pushing the organizations to have them. And so now, you'll see here that the result is that we still have those same boiler tube failure mechanisms. We still have those same HRSG tube failure mechanisms. We still have water wall and HRSG evaporator deposits. We still have failures in the phase transition zone, in the L-0 blades in the turbine. We still have FAC, and we still have copper deposition. It's not quite so frequent, but we still have it. And so we have to keep saying, why is that? And so we looked and looked and looked for many years to try to find why that is. And this is, I already gave you the message right at the beginning, right? To do with the basics. And so we call these basics in power plant chemistry repeat cycle chemistry situations. Repeat cycle chemistry situations. So that means that something happens in the power plant every day, or every week, or every month, and it's not correct. The basics that you're supposed to be applying to the plant are not applied properly. Okay? And how do we know that? Because I did analysis of over 200 failures in power plants all over the world. And what we found was that every one of those failures can be related back to multiples of these repeat situations. Multiples of them. Okay? So, all cycle chemistry influence failures, all those that I've showed you, and damage, can always be related back to multiples of these repeat situations. Okay, so now the question's for you. Tell me what a repeat situation is. What do you think a repeat situation is? In the basic things that chemists do in the power plant. Who's got an idea? Who's got an idea? You don't need to be quiet. Yes, go ahead. Have you got an answer? No? Second row? No? Yes? Have a guess. Have a guess. What's a basic thing that a chemist does? That you must be taught every day by a professor here. Right? Oh, anybody? What about on the front row here? You've had a good view, all you girls. No? Nobody got a guess. So what happens when you go to the power plant? How do you know that you're going to do the right things? When you go to the power plant, I want you to be doing these basic things every day, so that you don't have the problems. Any ideas? No ideas? On the back row? No? Okay. I better show you, haven't I? Should I show you? Yes, I'll show you. So these are the 10. These are the 10 basic features of a power plant chemist's job that are not being done. Okay? So, if you look here, do you think that you might need to know what the level of corrosion products is? You need some indicator to tell you whether the chemistry that you have on your plant is optimized or not. How do you do that? You measure the amount of iron in the cycle. Many plants that we go to do not measure the amount of iron in the cycle, so they don't know what the corrosion potential is. They don't do it every day, so it's a repeat situation. It could be too high, there's a guideline for it. It could be greater than 2 ppb every day, so that's a repeat situation. That's something that you need to know every day you're a power plant chemist. Second one, what about where this iron goes to? It deposits in the high heat transfer areas, in the water walls, and in the evaporators of HRSGs. And again, if you don't know what that is, then you don't know whether you can have failure. Failure always is preceded by deposition on the water wall. And so every day you don't know it, every day it's a repeat situation. It's a basic thing that you need to know as a power. And here at Moscow Power Institute, you should know it because we did some of the basic work just along the corridor here to measure deposition. Right, Tamara?
Yes.
We did just along the corridor, we measured it. And what about chemical cleaning? If you don't do the chemical cleaning properly, and you leave some deposit in the boiler, it's worse than it was before. It's a repeat situation. What about contaminant ingress? Allowing chloride or sulfate to come in from a condenser leak and not doing anything about it. And particularly if it exceeds a shutdown on a boiler. What about measuring how much goes from the boiler into the steam? Where does the chloride come from that goes into the steam turbine? It doesn't just suddenly appear, it comes from the boiler. So you need to know what that carryover is, and you need to measure it. What about air in leakage? High levels of air in leakage, especially on units that have copper, will give rise to the copper problems that I indicate. You need to know what that air in leakage is. You need to do something about it. What about shutdown protection? I already showed you that the basic reason the steam turbine fails are because they don't have any shutdown protection. Every day you shut the unit down, it doesn't have shutdown protection, it's on the path to failure. Inadequate online instrumentation. Not having sufficient instrumentation to know how your power plant works. And this is one of the biggest problems in a power plant for people like you, because they can't justify putting in a new instrument, a new cation conductivity, a new sodium, new whatever. And this is the one that I like, not challenging the status quo. You wouldn't believe how many power plants I go to everywhere in the world, and I say, Valeri, why are you operating with this chemistry? And they'll say, what will they say? Because I always operated like that. And they've been operated like that for 20 years. That's a repeat situation. Okay? So I call these the basics of power plant chemistry. And I hope that Professor Tamara Petrova tells you the same thing. Because this is one of the key messages that a student in a power chemistry student like yourself has to know when you go to the power plant. Because there's many things happen in a power plant. You have to do many other things as a chemist. But don't forget the basics. You have to remember the basics. These are absolutely the basics of chemistry. These are the basics of chemistry. And these numbers here, number 1, these are the most common. Not measuring the corrosion products, not having the right instrumentation, okay? Not measuring the drum carryover, not measuring what goes into the steam. So please, when you finish here and you graduate as super chemists from NIU, super chemists I emphasize, remember the basics that you learned here. You know, key message. You won't believe how many plants I go to that don't do these things. These are the plants that have failure, and you need to do something about it. And let's see. So in conclusion, I think that as we move forward, I anticipate that there'll be new chemistries that are added, and you'll get a salesman knocking at your plant door saying, this is the best chemistry that you've ever had. Make sure you understand what it is. Make sure that you know what it's going to do to your plant. Make sure that you do those basics of power plant chemistry. Because if you don't have any indicators to tell you that this new chemistry is good or bad. Okay? And I think that's everything. Hopefully you'll have a very nice little plant like this. This is the same cycling plant, but he now understands all that chemistry. And he's doing all the basics, right? He's not allowing any repeat cyclochemistry situations to exist in his plant, or in her plant as well, sorry. In her plant as well. And he's almost certainly adding a little bit of oxygen here because that's the best that there is. And he's a very happy little guy here. And he can cycle back and forth, no problem at all, if he has the chemistry right. But it's in your hands. Okay? So, Constantine, I think that's about all I have to say. If anybody has any questions or comments, I'm more than willing to answer them.
Уважаемые коллеги, пожалуйста, если есть вопросы, можно даже по-русски задать, попробуем перевести. Ну что, кто смелый?
How many of you have already been in a power plant? How many have you been in the chemistry laboratory? No.
No.
Have you been in a power plant? I don't mean the power plant here. I mean in a yes. Yes. And what about over here? Yes. You people here have been in power plant? No. Yes.
I've been in a power plant, but not as chemical specialist, but as electrician.
That's what?
As electrician.
Electrician. Okay, good.
So, thank you very much. Very nice lecture.